Humanoid robot legs come in many forms. We will go over some of the most popular humanoid robot leg designs from research robots like UCLA Artemis, MIT Humanoid, Berkeley Humanoid, and USC Hector Humanoid to industry robots like Tesla Optimus, Figure AI Helix, Unitree G1, and Kscale Labs Kbot. By the end of this video, we will understand how these robots differ in joint configurations, actuator selection, gear ratios, and driving mechanisms. All right, let's get started. If you're new here, this is Kevin. I've been doing robotics and AI for 10 plus years and have lots of resources on my channel. I also have a course on robotics and AI that you can check out on my website at kevinwithrobotics.com. So the first robot we're going to talk about is a Berkeley humanoid robot. And you can see here, this is a pretty miniature sized robot that goes around to the waist of the person. So it's one of the smaller robots, but let's go ahead and take a look at the design. So if we look here, we see that this specific robot, we see the configuration that it has here. If we look up on top, this is the HR hip roll, hip yaw, hip pitch. So the roll, pitch, yaw, this is the three main hip joints. And you can see that they have the torque specifications here. These are specific actuators that they developed on their own. All of the gear ratios here is 9:1, and you can see the range of motions here on the right column. So we're going to be covering the differences between the configuration of this robot and the other ones, but you can see that after the roll, yaw, pitch, we have the knee pitch and the ankle pitch and ankle roll. So some things to notice about this design is that if we look here, down here, they put a motor directly on the bottom here. So they have a roll that will help you with the balance. So you'll see later on that some robots have this and some don't have it. And another thing to notice too is that if we look here at this design, you can see that where the knee actuation is happening here, they're actually using one motor attached to one link to drive the one of the knees here. So this is the top motor, and then a second motor here, they have another linkage to drive the ankle. So the reason why they have the actuators shifted away from the actual joint locations is to reduce the inertia of the system. So that helps with some of the speed responsiveness as well as the actuator torque requirements. So next up, we're going to take a look at the USC Hector robot. So this one also is a miniature size one. And you could see, if you look closely, you might realize that this is pretty much a Unitree dog retrofitted into a humanoid robot. So if we take a look at some of the design, you can see here that if you look at the peak torque, the Unitree actuators, they don't give you the rated torque, so they only give you the peak torque. So that's why I have the peak torque listed, but it goes up to 33.5 peak torque. And the gear ratio, again, is also 9:1. And you can see the configuration here is a yaw, roll, pitch, and then we have a knee pitch and ankle pitch. So this design, unlike the previous one, this one relies on some belts here. So they have a belt transmission and also some linkages to transmit some of the joint motion. So here's a look at the specific actuator. They call it the A1 motor from Unitree, and they use RS-485 communication. So you could go ahead and take a look at these actuators if you're interested. The next one we're going to talk about is the one from MIT. So this is a MIT robot. You can see this one is a very similar size to the previous one. So what you're going to notice is that there's a lot of research robots that's miniature, and then a lot of the industry ones are actually bigger. So we'll take a look at that very shortly. But the specs for this, you can see we have a yaw, roll, pitch configuration. The pitch one here has a much higher peak torque of 68. And we have a knee pitch of 136 with ankle of 52.2. So these specific actuators, they designed by themselves, but you can see the shape of this looks very similar to the previous one. But if you take a look here, these are the two actuators that they've developed. So you could look up their paper if you want to learn more about their actuators. This next one here is a UCLA Artemis robot. So this one is a pretty unique design, I would say, compared to the other ones. This one is a research one, but it's a much closer to, I would say it's above a medium-sized robot. So it's a bit in between a medium to a full-size one. And let's take a look at some of the specs here. So they designed their own custom actuators. And you can see that here we have a hip, yaw, roll, pitch. And you can see the torque here with knee pitch and ankle pitch. So this one is a 5 degree of freedom. They're missing the roll that we saw in the Berkeley Humanoid, but you can see that a lot of their gear ratios here are relatively low. It's a little bit higher than the ones we just saw. So they go up to 14.5 here, but the hip and knee is much lower at around 5.9. The ankle pitch, however, goes much higher, up to 50, and that probably has to do with some of the responsiveness and the power needed. Most of the power is probably going to come from the knee and hips, which is probably why they made these design choices. So if we look at some of the design, they have this linkage here that drives the knee with this actuator. So if we go back, you kind of see they have a similar one down here at the ankle. So they have this similar design for the knee and for the ankle. So the reason why you might want to choose a linkage design is the similar reason which I described previously. So we've seen the belt like the Hector robot, and then we have this one and the Berkeley one. They all use the linkage design, which helps with some of the rigidity and stiffness, which sometimes the belts could be hard to model. So I think that's probably the reason why they went with such a design. And some of the actuators they use, they talk about it, is from the Bear actuators. The Bear, it was originally developed at UCLA, and then the Westwood Robotics company spun off into a company, and they sell some of these actuators. So the specs are not exactly the same. They're kind of similar, but you could probably use these to build your own robot as well. By the way, if you're trying to 3D print something and don't have access to a 3D printer, make sure to check out PCBWay, the sponsor of this video. Just come up here to CNC 3D printing, choose 3D printing. All you have to do is take your STL file, drop it in here, choose the quantity, material, color, and process. If you have threaded holes, you can add threads and inserts in them. They come out really nice, so it'll save you time. You don't have to deal with the nuts inserting them. And just go ahead and come here and submit your part for review. So I'll be making a humanoid robot very soon. So if you want to build it on your own, you could come here and check it out. Next here we have Kscale Labs. They have a robot here. It's a pretty close to a full-size humanoid robot, which they call Kbot. And you can see here they're demoing some of the controls. It's a standing policy where it's just trying to stay still using RL. And you can see that the person will try to kick it around, and you can see that it can try to stabilize here. So that's showing the RL policy in action. So if you look at the specs now, you can see these are the motors they use. It's from Rob Stride, and you can see the rated torque for each one. Similar to the other ones, you can see the gear ratios they use is very low. It's 9:1 or lower. The ankle pitch here happens to be the lowest. But you can see here that the configuration we have is a pitch, roll, yaw configuration. And you can see these are the range of motions here. So you can see right here, these are the actuators they use. They come in a lot of different sizes. So you could use these if you want to build your own robot as well. So next one I want to talk about is the Unitree G1. So this is their educational type robot here. And you can see right here, they're demoing a lot of kicks. This is the most recent demo actually, and it can easily stand up with various sorts of kicks from any side of any force. So this is actually quite impressive. I'm very impressed with their latest development. But you can see here, these are some of the joint, torque, and gear requirements here. So you can see here that we have pitch, roll, yaw configuration. You can see these are the torques. These torques I actually got from their URDF file. So they actually don't list it out anywhere, but you could read through their GitHub to get that information. But you can see here, these are the joints laid out here. This is a full 6 DOF robot, unlike some of the other ones we saw. One thing that's really special is how they configured their pitch and roll actuators here. So they have 2 motors actually right below the knee, unlike some of the previous one where they try to move it above the knee. And you can see the back here of the robot. These are how some of the joints are configured. So come here to their document. You can see exactly how the joint works. So they have the 2 motors here with 2 linkages, and the foot at the bottom here, you can see is attached to 2 points down here. If I zoom in, you can see these are the 2 points. So we have a pitch and roll joint, which is intersecting. So it's basically a universal joint that allows the foot to have 2 degrees of freedom. So the main purpose of the roll, if you think about it, is if you're standing on 1 foot, then being able to pivot, right and left allows you to balance on 1 foot. So that's some of the advantage of this. And you can see here, this is a simulation of the foot being actuated. And you can see they're pulling this in Mujoko, but you can see how the foot works. And it has quite a bit of range of motion. So I would say this design can be a pretty good choice if you're trying to have a 2 degree of freedom ankle. But later on, we'll see some of the other designs can implement the same behavior using a different mechanism. All right, so next up is Tesla Optimus. I think everyone probably knows this robot. But you can see here, this is their Gen 2 robot. One thing about the Optimus robot in their design is they actually use linear actuators. You can see a lot of the older designs, like some of the Atlas, they use hydraulics, and then they've been moving to more electromagnetic type actuators like brushless actuators. But you can see here, they've actually integrated some custom linear actuators to their foot as well as their thighs as described in the patent. But let's go ahead and take a look at some of the specifications here. You can see these are all the joints laid out as we talked about, but they have a configuration of roll, yaw, pitch, and then we have knee pitch, and ankle roll. We're going to talk about some of the differences between the different designs and some of my thought process on why that might be. But you can see here, these are the actuators laid out. And if you dig through their patent, they specify some of the torques of their actuators. They don't really point out which one goes to where, at least the patent I saw. Maybe there's some other patents, but you can see here on the top is their normal actuators, and then the bottom is their linear actuators. So you can see they go up to 180 Newton meters and 8,000 Newtons for some of the linear actuators. So it's some crazy strong actuators, and you can imagine a lot of times when you're running or jumping, you could see several times the force of your body weight. So that's probably why they need such a high actuator to move their robots. But you can see here a closer look at some of their patents. You can see how their linear actuators are laid out here, and they have this very interesting part of their design for the knee and the hip where they have the roller. So that's kind of how they do the bending motion for some of the 2 main joints. And the feet here too, they actually have 2 linear actuators. So it's very similar to the Unitree design, where at the base of the foot, it's like a universal joint where it has 2 degrees of freedom. The only difference I would say is they're using linear actuators to actuate it. And their pitch actuation too here, they're actually embedding a linear actuator here to do the actuation. And the next one I want to talk about is the Figure AI robot. You can see this is a video here of their locomotion. And I want to point out something that's very interesting about their gaits. If you look at the robot walk, in some views you can see a little bit better, but you'll notice this weird tilting, and you can see this robot here, the way the hip tilts, it kind of sways front and back and tilting right and left, up and down. And I think it has to do with their degrees of freedom. And please correct me if I'm wrong, but I think they only have 5 degrees of freedom for their legs. And I'll break down the ones that I think I see here. So I think I only see hip, pitch, roll, hip, pitch, roll, and I don't see a yaw, because if you look closely here, this actuator here is a pitch. We have the roll here that swings your leg out to the side, and we have our knee pitch. They actually have the actuator directly at the knee, so a lot of the other ones, they would move it away from the knee to reduce the mass, but it seems like they don't really care. And we also have an ankle pitch. I think there's an actuator in the calf somewhere here. And then the ankle roll is actually directly on the feet. So I would say their design is very mass heavy at the joints. They almost don't move any of the joints actuators away from the joints. So I think they didn't really care about that for their design. So let's go ahead and compare some of the leg joint configurations and kind of summarize what we see here. But for the different robots here, we have a category of 6 degree of freedom joints. So we have the hip roll, yaw, pitch collection here is we see it on the Berkeley Humanoid and the Tesla Optimus. So they opt for this configuration. We also see a pitch first design, pitch, roll, and then yaw. So we see this in the Kbot and the Unitree. The main difference with the Kbot is that they actually don't have the ankle roll. So you might lose a little bit of stability control, but it seems like they're not really trying to target that, probably because their main goal is to reduce pricing. And we also have 5 degree of freedom robots that we saw here. So the USC Hector, MIT Humanoid, and the UCLA Artemis, they have a configuration of using the yaw, roll, pitch. And the figure AI, they follow a pitch, roll, and then skipping the yaw. Again, I think they're skipping it, but you could let me know if I missed the actuator. So here you can see these are the 2 main configurations that we saw that are pretty popular among the humanoid robots. So on the left, we have the pitch, roll, yaw. And on the right, we have the roll, yaw, pitch. So you can see that the roll, yaw, pitch configuration, the Tesla Optimus opted for this sort of design. And then for a thing like the Unitree, we have the pitch, roll, yaw configuration. So one thing to note about the differences between the two is I would say the main thing comes down to the packaging. So you can think about here, like the dotted line here, this would be the center of the robot, and we would be looking, for example, at this would be the left leg. So if we see the left leg, one thing to note already is that for this axis, which is the pitch, the next one, which is the roll, you'll notice that if you're to rotate the pitch actuator, one thing is that if you have a right and left pitch, so if I drew another actuator here, you notice that the 2 pitch actuators can be sandwiched together to have a very tight packaging. So that's one thing to consider. And then also, if you're to rotate your pitch, the only part that would really have any clearance, you can see that this actuator here is going to be, if it's a similar diameter, is going to be within that rotation. So you don't really need to have too much clearance around there. Now, if we take a look at the roll, yaw, pitch configuration, again, this could be the leg here that I draw out. You can see that if we have the roll first, then if this whole thing is rotating outwards, then if it rolls upwards, then you're going to have this whole part of clearance if it needs to pivot up. So I would say in terms of the amount of clearance needed, the roll, yaw, pitch configuration will probably require more clearance just based on how the joints are configured. And you can see with the pitch, roll, yaw, if you do that same pivot rotation, it's not going to hit as much because this pitch joint is on the outside and you won't really have much things hitting because the only part that's moving would be the thinner part. So that's one immediate thing that I see. But in terms of the degree of freedom, there's not going to be too much difference because the the hip is essentially a ball socket. So a ball socket, you're going to need 3 axis, intersecting axis either way to form the ball joint. So either way, they're going to have that sort of configuration. But another thing I would say is the main difference between these 2 configurations, for example, is the pitch. Because this pitch actuator is at the very last, whereas this pitch is the first. So you notice these are the main differences, first and last. The pitch actuator that's going to be first is probably going to see a much higher torque requirement because you have all the weight of the leg that's after the first actuator. Whereas this pitch here, like the Tesla, if the pitch is last, then it's going to see less of the forces. So these are some of my immediate takeaways from the difference between the pitch roll yaw configuration versus the roll yaw pitch configuration. All right, so that's it for this video. If you want to check out some of my other builds, I have a humanoid robot arm video that I posted a couple months ago and a bunch of videos on actuators. So I plan to create some videos where I build out a humanoid robot leg. So I'm going to have some deep dive videos like this one here where I walk you through step by step how I design the robotic leg. So you could go ahead and join my membership here. Then you'll have access to those deep dive videos. So if you found this video helpful, give a like and subscribe, and I'll see you in the next one.